Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So today I'm going to be talking about how to improve packet delivery efficiency using multi-radio diversity in wireless LANs. So let's get right to it. So the motivation is driven by the many new exciting applications that are appearing on the market today. Soon people will be talking on the phone, watching TV, playing video games, sharing music, and so on and so forth on these wireless infrastructure, wireless networks. And these new types of application place high demand for performance. Naturally, people will want their wireless network to perform just as well and just as reliable as their wired networks. So what this means is high throughput and good coverage everywhere. As we all know very well, the problem here is that wireless channels are loss prone due to a number of factors that you know very well. And these factors cause very inconsistent and poor performance that are apparent in today's network. So just to give you an example of how bad things can get in real-world setting, what I did is I performed an experiment using my laptop, and then I connect with one of the access points, and I'm trying to upload UDP packets as fast as I can. And then in this experiment, I lift my laptop up and start moving with it in a 1.5 by 2 meter squared area. And I measure things like throughput and loss rate. And the top graph shows throughput fluctuating wildly between 2 megabit per second to 18 megabit per second. So this shows that the area is quite unevenly covered. The performance is quite inconsistent. The bottom graph shows that the loss rates range a variety of rates from 15% to 42%. Again, this shows that the area is fairly poorly covered and leading to poor performance. Yes. One second. Yeah. Yes. Yes. It's a number of frames that got received correctly divided by time. So I transmitted 100,000 packets in this experiment. Yep.
So in that case, is the throughput directly related to the loss rate?
Yes, it's somewhat related, and it's also related to the rate adaptation algorithm, which I will go over later on in the talk. If I didn't move my laptop, it would be fairly flat. So in this situation, I'm trying to measure coverage over an area. So
Just 1 meter, right?
yeah, 1 meter by 2 meters, so it's not very big. It's about yay big. Just to see how performance varies within this area. Okay, we should move on. So since loss causes poor performance, one of the most important criteria for designing high-performance networks is to design mechanisms to overcome losses. So, however, current approaches have their drawbacks. For example, we can apply FEC, and as you know, FEC has overhead, and it's hard to do on highly variable channels. Yep.
So really whether what matters is the time scale there. And if the time scale is sufficiently long, then it's highly variable, that you might get a time approach.
Yep.
What seemed to have shown in the previous slide, the time scale was long because it was over 1 second average.
Yep.
You needed one with 15
Yep. So later on, I will have results that shows the other case.
Okay.
Yep. So second, if coding, so another approach to kind of high losses is to retransmit. But sometimes you can retransmit all you want and nothing can get through. So retransmission turns out can be wasteful at times. Yep.
So wasteful with respect to power?
With respect to, no, not power, but with respect to consuming the airtime. So you're transmitting air, you're consuming airtime, but nothing is getting through.
Right, but now you have this kind of implied, but the outage is only going to be local to that receiver, not to other receivers in the neighborhood.
Right.
Yeah, that wasn't on the previous one.
Right. So we're trying to motivate things.
Okay.
Yep. You're right. I mean, there could be other receivers that are suffering from the same thing. So in general, if you do retransmission and if there's outage, you're consuming bandwidth, and then it affects other people because this is a shared medium. Yeah. So, and then the third approach is to adapt bit rate. Again, this is hard to do if the channel is highly variable. And as I explained, it has the side effect of slowing other clients because as you slow down the bit rate, you're consuming more airtime. And if you consume more airtime, then other sender gets to transmit less. And then it turns out there are some cases, I'm going to show later, some cases bit rate adaptations just don't work. I mean, you would think that it will hide losses, but it doesn't. So our belief of recovering losses is that today's mechanisms do work, but they're not working well because they're inherent constraint in today's infrastructure. And that constraint is that each wireless client can only use one access point at a time, whereas multiple access points are available in real life. So typically what happens is a client comes in, and does a scan, and then it associates with only one access point in the system. And the idea here, the reason why we do that in the current system is because all the access points work independently. There's no coordination. So you'll designate exactly one access point so that you don't have multiple access points to forward redundant packets and cause confusion. So over time, this client can move to another location, and then the client can perform a handoff, do a scan, perform a handoff. Again, it maintains only one connection where multiple access points are available in the area. So the thesis, the hypothesis of my thesis is that losses are path dependent, and moreover, they're bursty. So meaning if you use only one path, you're going to suffer from losses over time. And then my hypothesis is that we can use path diversity. By using multiple access points, multiple radios, we can overcome some of these losses. The contribution of my work is the experimental evidence to confirm my hypothesis and a practical system that takes advantage of path diversity in the receiver side as well as in the transmitter side. Yep. Yes, it's very similar, but the major difference is MIMO is constrained to the footprint of the device because you need to have tight synchronization with the antenna, whereas I try to coordinate multiple things in the widely separate over the network. Widely separate. It's complementary. That's what I believe. Yeah. Yep. Yeah, so it's receiver location dependent. So path dependent, we're trying to capture all of that in the sense that there's different receivers have diversity as well because the electronics, the noise in the electronics are random, for example. So they're receiver independent as well. So it's I try to capture all of that. Different receivers also, I count that as a different path. Yeah, does that make sense? So the basic higher level overview of my system is I deploy a centralized controller in the infrastructure to coordinate reception and transmission in the network. So what happens in this case is uplink transmission will succeed if any of the access point receive the transmission correctly. For downlink, we use the centralized controller to intelligently pick and choose the best access point to transmit each transmission to improve the delivery rate. And using this system, we have achieved a factor of 3x throughput improvement. And this is done without consuming much extra wireless bandwidth. So the whole premise, the underlying assumption of my system is that there's path diversity or receiver diversity in the network. So one of the early experiments that I did is to confirm if this assumption holds. So what I did is I ran an experiment with 6 stationary receivers and 1 stationary transmitter. And I did 802.11a broadcast experiment. What I did is I looked at one specific pair of receivers and I computed the frame loss rate of one of the receivers of the individual receivers and the joint frame loss rate. That is, what is the rate that both receivers sees a loss for the same transmission? And then I repeat this computation for all 6-choose-2 combinations, and I have 15 pairwise combinations. And the main idea is I want to see if this relationship holds. If the product of the individual frame loss rate equal to the joint frame loss rate, then we can establish loss independence, or it suggests that there's loss independence in the thing. So here are the results. So on the y-axis, what I plot is the product of the individual frame loss rates for these 15 pairs, and on the x-axis is the joint frame loss rate. And this scatter plot pretty much shows that the values are pretty similar, the products and the joint frame loss rate. So the reason, again, is because there's paths are different, meaning that the multipath reflections, multipath fading is fairly different for different receivers at different locations, as well as the noise in electronics are also independent. Yeah, so we're trying to isolate path-dependent, like physical effects, as opposed to other effects, say from contention. So we're not dealing with contention at all. Yep. 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 Yeah. I'm glad it generated good. So we've established some sort of path diversity in our experiments for receivers. So what about, we now turn to transmitters. Do a similar relationship hold? So for transmitter, we conduct an experiment involving two transmitters alternating transmissions to a single receiver. AB, like so in the illustration. And what we looked at two different types of metric. One is the auto-conditional loss probability. Given that a frame has been lost from path A, what's the probability that the next frame from path transmitter A is going to result as a loss? And we do this for over different time scales. And then we looked at another metric called the cross-conditional loss probability. So given that there's a loss from transmitter A, what's the probability of getting a loss from transmitter B? And we do that for next over different time lags between the two loss events too. So the reason why we're looking at, so cross-conditional loss probability shows independence, but why are we interested in auto-conditional probability? The reason why we're interested in auto-conditional loss probability is because in our system, we can only have one transmitter transmitting at a time. We cannot have simultaneous transmitters. So we have to compare the two loss probabilities to see if there's any benefits of doing this kind of like fine-grained path selection in transmit diversity. So here are the results. So first, I plot the auto-conditional probability for path A, and the y-axis is the conditional probability of loss. X-axis is time lag between the two loss events, and these are expressed in the number of frame transmission between the two loss events. So at large lags between the two loss events, the auto-conditional loss probability converges to the average loss rate for the thing. So it means that if losses are far apart in time, they're pretty much independent. They're just the average of the single path. But as you move the lags shorter and shorter between the two loss events, you see the conditional loss probability goes up much higher than the mean, which means that the losses are bursty. If you see a loss now, the chance of the next loss is high. Yep. The horizontal is, so we're alternating transmissions. So time between transmissions for one, so 1 unit is 4 milliseconds. Sorry, for 4 milliseconds. Yep. And then I plot the same metric for path B, and we see a similar trend. And now we look at the cross-conditional probability. So what we hear, in contrast to the loss conditional probability, we see a flat curve, which means that losses are not affected by the other path, transmission path. In fact, when you now compare the auto-conditional probability and cross-conditional probability, these results suggest that the best strategy to use is if you see a loss in the current transmission, you should just switch path. So, Yep. So what happens is that sometimes there are, okay, I forgot to mention one thing. So in this experiment, I did a mobile experiment, because if I didn't do a mobile experiment, then things are just flat. But then when I do a mobile experiment, what happens is I would go into corners in this area. So it's the same area, corners in the area that are not covered by one of the transmitters, basically. Yeah. No, yeah, environmental, physical, yeah. So I've shown some evidence of path diversity. How do you take advantage of it? So for the rest of the talk, I'll concentrate on receive diversity, because that's where we get the most benefit. And it works for the uplink and downlink direction in the system. And then if I have time, I go over quickly the transmit diversity of the system. And finally, I'll talk about related work and end with summary and future work. So receive diversity. How does our system work for the receiver side? So this slide shows an example of how receive diversity works in the uplink direction. In the uplink direction, we have clients to associate with the primary access point. And then we've deployed additional secondary access points that are tuned to the same radio frequency as the primary access point. And in this case, a transmission succeeds if either of these access points receive the frame. So an example of how this can improve performance, suppose the loss rates are indicated as shown to each of the access points. If we assume loss independence, then the loss rate would reduce from 10% to 2%. And then there are times when multiple access points, of course, receive the frame correctly. So in this case, you have redundancy. So a simple way of solving the problem is to deploy a centralized controller to filter this redundant frames out. Later on, I'm going to show how we use the MRD controller to do things for retransmission as well as rate adaptation, and also do frame combining in the case for error correction in the case that none of the access points receive the frames correctly. So before going on, I want to go over how this system is deployed in a real system. Is this compatible with the cellular architecture in our system? So the typical there are many ways of deploying the system. One of the ways of deploying the system is to add additional secondary access points in each cell, as shown. So you have your primary and secondary access point within each cell. Another approach is to do this channel overlay. So you deploy multiple radios, and these are received radios, passively received radios, in each of the access points. So we distinguish between the primary and secondary radios. The client would associate with the primary radio in the access point, while the secondary radios on the other access points would provide the alternate receive paths in the system. So there are different trade-offs between the two, namely you need more specialized device, so on and so forth. And then on the left-hand side, you need more wiring and so on and so forth. So the point here is like there's a flexible way of deploying the system. So what are the challenges? Well, the main challenge that we need to figure out is what happens if none of the multiple radios receive the transmission correctly. How do you handle that case? Turns out from experience that there are a large fraction of frames that are received, even though they fail, but you receive them as corrupt frames. And within these corrupt frames, it contains a large number of bits that are actually that are correct. So we're figuring, like, can we combine multiple corrupt versions of these transmissions and then correct the errors? For this, we developed a frame combining algorithm. Second is, how do you handle, if the frame combining algorithm doesn't work, you need to retransmit the frame. And how do you do this in presence of multiple radios in our system? For this, we developed a special feedback protocol called request for acknowledgement. And third, if error correction and retransmission don't work, then we need to adapt the bit rate. How do you do this when multiple radios are around? Yep. Yeah. So I'm not going to go over the details in the interest of time, but what happens is you associate with one access point. So you use link layer ACK with one access point. If that one fails, then you ask request for acknowledgement. You ask the MRD controller for feedback. Does that make sense? So there's no ACK implosion.
So what happens?
Yeah, retry count is set to 1. So I'm doing retransmission at the MRD layer. So as I was saying, I'm going to concentrate my focus on the frame combining scheme and the rate adaptation scheme. Yep. At the controller. All of these things are happening at the controller, involves the controller. It starts with D. DRAC. Yeah, so it's exactly that architecture, but I'm just applying it in the specific in the application of improving performance. So they're looking at a centralized management architecture to do things like management, security, handoffs, and so forth. I built the whole thing, yeah. I have a picture of it later. So frame combining. So frame combining is this concept of combining corrupt versions without having to do encoding at the center, combine the copies and generate an error-free version of it. So you're getting something for free by spending computation in the infrastructure. So frame combining can work fairly well when you have 3 versions of the frame. What you do is you look at each bit and you vote for the majority. But there are many instances where you only get 2 frames. For example, you only within reasonable reception range of 2 access points, for example. In this case, you need to do something called bit-by-bit frame combining. And I'll show you how this works through an example. So in this example, the transmitter transmitted bit patterns as shown, and each of the receiver receive a erroneous version of the transmission. First step of bit-by-bit frame combining is to run XOR between the 2 frames to identify the locations where the values disagree with each other. And then we generate test frames by combining different combinations of the values at the disagreeing position, and then run the CRC checksum on it to see if the combination was the original transmission. And if the CRC checksum doesn't work out, then we try another combination. For example, we take another 2 bits from R1 and 1 bit from R2, and then we combine the test frame. In this case, it doesn't check out. And then we keep trying until, hopefully, it will try to check out. Mm-hmm. I will talk about that later. It's exactly, you hit the right mark. So I'm going to talk about first how this fails. So it works. This scheme works on the assumption that the bit errors are not correlated, meaning that if the errors, if the 2 receivers agree on a bit error, then you would never detect it in the first place. So you would never be able to correct the frame. It will show up in the CRC, but the CRC won't check through. Won't. Right. Right. Yep. So the problem is, as you pointed out, this exhaustive search is very expensive because it's exponential, and there can be more than 100 bits that disagree with each other in the frame. And another thing I think you're mentioning is about if you repeatedly check the CRC, would you get false positive? The answer is yes, you would, but the probability of getting more false positive is still quite slim after you work it through. So So this is a problem. The computation complexity is a problem. So what we do is we go back to the data and try to analyze to see if we can do something more intelligent. So what I show here is a histogram plot of the bit errors of 18,000 erroneous frames. On the x-axis is the location of the bit error within the frame. So you see this distinct pattern of having more bit errors located in certain location. And these bit errors have a certain width. So the way to explain this is that this experiment was conducted using 802.11a at 48 megabit per second. So they happen to encode 192 bits per OFDM symbol. And then when the receiver doesn't decode the symbol correctly, you actually nail down 192 bits. So to find out how these bits positions are correlated with each other, we again do this auto and cross conditional loss probability analysis for bits inside of frames. Again, we see the same thing. Bit errors are bursty, but they're not highly correlated with each other. So what this suggests is that instead of doing this thing bit by bit, we can do by chunks, by blocks. And as you can guess, what you do is you divide a frame into a limited number of blocks so that you can bound the computation complexity. And then you can assemble a correct test frame by a combination of these blocks. But what are the consequences of this algorithm? Well, one consequence is, well, okay, first of all, how does algorithm fail? So this algorithm fails when you have errors in the same block. So no matter which block you choose from either frame, you will always include an error bit. So the consequence of this algorithm is as you increase the block size or lower the number of block divisions, the failure rate goes up, right? Because a larger block can contain a bit error and so on and so forth. And another consequence of this algorithm, or this thing that depends on, is that it depends that the errors are clustered together. If they're more spread evenly over different blocks, then you will increase the probability of getting errors in the same block position. So in a nutshell, the consequence of running this block-based algorithm is that you have these two parameters to worry about. Yep. Yeah, so that is more on the flavor of forward error correction. So we're trying to do this thing without encoding, but certainly if you encode this intelligently, you can get more gain. We haven't looked into that in more depth.
I'm saying it seems like you're already in that framework.
Yeah.
The fact that you have the CRC
Right.
not checking two different codings.
Yep.
There's two different words that.
Yep. Yeah, it is an interesting direction. We just didn't go that one step. Yep. Yep. So basically, this is really a major function of this because we don't have control over the burst length. So we try to pick the maximum n that is allowed by that we have computation power-wise. So, and then we also develop a model to evaluate. We generalize this framework as a ball placement problem to evaluate and develop a numerical model to evaluate how the failure rate varies with these as a function of n, b, and b. Okay, so moving on. There are times when the frame combining algorithm doesn't work, so you need to retransmit. And I'm not going to go over the detail of the algorithm, but I'm going to talk about the problems that you need to think about. So the conventional link layer acts don't work because the final status of each transmission is only known to the controller. So what you can do is you can have two levels of acts. One from the MRD controller and one from the link layer from the primary access point. But however, like having two levels of ACK are kind of redundant. You want to optimize this in the sense that when the channel is good, you don't want to keep sending these MRD feedbacks to the controller. How do you do that? Well, one way of doing it is to try to disable the link layer ACKs completely. However, this introduces a problem when you have multiple clients, because now you don't have the link layer feedback to do contention control. So what we did instead, we developed a protocol to solicit feedback only in the case when the channel is bad, and makes everything more efficient. Yeah. Okay, so the idea is in the link layer contention control, it relies on the link layer ACK to determine if there's a loss, and also relies on the same bit of information to determine if there's contention. So it kind of conservatively assumes that if there's a loss in the network, then it assumes there's contention. And then in that case, it will try to increase the backoff window, randomized backoff window in the next time it tries to transmit the packet. Does that make sense?
That makes sense.
Yeah.
I'm actually still left wondering if you have something like RTSP gets enabled, you also get that.
Yeah, so we try to avoid doing that because RTS is very expensive.
Okay.
Yep.
But the access point is good.
Ah,
Access point is keep the same.
yep. So there's one case where it doesn't work. The case it doesn't work is when there could be a case where the forward data frame goes through, but the ACK doesn't come back. So from MRD controller's point of view, there's no loss. But then the sender thought, what am I supposed to do with this frame? Because as far as I can tell, the link layer is telling me that the frame got lost. So should I retransmit or should I not retransmit in that case? Because I don't have feedback. Right. Yeah. No. So what happens is these are cumulative ACKs. So I'm getting into details here. So you keep asking for feedback, and then these ACKs are coming back periodically when the channel is bad. So the request for ACK flag is kind of like a signal to the MRD controller saying, I'm not sure what the state of the channel. Give me some feedback periodically. Start giving me feedback periodically. Right. Right. Yeah. Oh, each of these boxes? Yeah, so, right. So you, yep. Yep. So that's a distributed approach, and that can lead to, a distributed algorithm can sometimes lead to contention, added contention, and things like that. So it's actually, we can take it offline. There are many ways of doing it, and we've taken one approach, right? Yeah. 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 So you have to do this distributed. Yeah. Yeah. Okay. No. Right now it doesn't. MRD and the PAB can coordinate, but yeah. 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 Okay, so moving on. Rate adaptation. So for similar reason that retransmission don't work in MRD, rate adaptation don't work in MRD because the standard rate adaptation algorithm only reacts to one receiver, whereas in MRD you have multiple receivers. So I just want to go over an example to really let you understand what the implication of this rate adaptation is when you have multiple receivers. So let's assume in this example that we have two receivers, R1 and R2, and then we have a choice of two different bit rates. And then let's assume that the path to each of the receivers suffer a loss rate as shown. So in this model, it basically means R2's path is twice as worse as R1's path because all the loss rates are twice as large. And then by independence assumption, if you use MRD, the loss rates are just the product of the two individual loss rates. And then from these loss rates and then you multiply it with the bit rate, you get these throughput results. Okay, so in the standard rate adaptation algorithm, what happens is it only looks at the loss rates in the individual receivers and reacts accordingly. And then so at 24 megabit per second, it sees a 33% loss for R1, which is greater than a certain threshold, 25%. So the way we derive this threshold is you want to use the lower bit rate when the loss rates fall below. When you multiply the loss rate against the current bit rate, it falls below the next lower bit rate in your scheme. So you're trying to maximize throughput, right? So when you look at the individual receivers, both of them sees losses that are higher than the threshold. So naturally, the algorithm would choose the lower bit rate. In this case, if MRD uses that scheme, then it will choose a result that gives you 17.6 megabit per second throughput. However, if you modify the scheme so that it reacts to the losses seen at the MRD controller, then it sees a lower loss rate than either of these receivers. In this case, the algorithm would pick the higher bit rate, better performance. So this scheme works well, but actually if you step back a little bit, it has an implication about how we manage link quality today. So in today's world, you try to adapt as much as you can, do rate adaptation as much as you can before you select alternate paths. But in my case, in our system, we take the opposite approach, which is we first use multiple paths and then run rate adaptation on top of it. What this benefits is that by using multiple paths first, you can lower the loss and loss variance in your channel. And then that would help make the rate adaptation algorithm work more efficiently at the higher layer. Go ahead. Yep. Sure. Oh, you mean when the access points are tuned to different channels? Okay. I have results. Yeah, I have results to answer your question. Just hold on to that. Very good question. Yep. 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 Oh no, then there's like yet another higher level thing, which is the handoff algorithm. So if it's over the long term, the third access point is providing a better path, then I would do a handoff. Yeah, 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 yeah.
What we need to do that handoff is cumulative successful probability. It really depends on how well all three of those guys receive them.
Yeah, so that's one of the extensions that I want to look at as future work. It's like right now I'm preserving the handoff so that you can preserve frequency reuse in the current existing scheme. So the longer term vision for this system is to create a purely channel overlay system so that you don't have to deal with the handoff at all. You just use the centralized controller to determine which set of access points you should be communicating with at any given time. Yeah. So to test how, well, what was that?
One of the things that cellular gives you is a mitigation difference. But if you have a single channel system, then you aggravate it.
What do you mean by that? I'm not.
The defensive factor is a lot more than that.
The interference between co-channel interference you're talking about. Okay.
Different,
Yep.
right?
So the thing is, like, in order to build this system, you have to think about load and how you balance load between the channels. So if you have two guys that are operating in the same frequency far away, then it's okay because they're far away, so you can do spatial reuse. But as these two guys move and meet, then the system should be able to infer, oh, these two guys are they're interfering with each other, meaning that they're contending with each other, okay? Then they should just switch one of those guys to a different channel. So I haven't built that system yet, but that's kind of like how it should work. So I built a test bed testing how receive diversity works using Linux, using the Met Wi-Fi Athros platform. And then in this experiment, it is a mobile transmitter laptop. It's in fact this very laptop here. I move it around within the small area and transmit 100,000 UDP packets with 7 retries. I let the sender to adapt at all available bit rates, talk about how the laptop is moving already, and I compare the 3 different schemes. R1 and R2 are the conventional single pass schemes, and MRD is the MRD scheme. Repeated this experiment 5 trials each. Here is the throughput result. So MRD provides a factor of 2.3 improvement in this set of experiments. And different color bars shows different trials, so you can see the variations between trials. And another thing to notice here is that the improvement is greater than the sum of these two. So if you were to install multiple radios and to configure to operate at orthogonal frequency, and if you assume that they never interfere with each other, then this single pass system, the sum of these two systems, is not as good as MRD. So why is that? This is quite surprising. So the reason is because we've made rate adaptation much more efficient. To illustrate this point, I plotted the CDF of the transmission bit rates. And you can see for the single path cases, it uses a variety of bit rates from 6 megabit per second to 24, but it's spread all through the different ones. But then for MRD, it was able to reduce losses to a point that it can maintain a 36 megabit per second bit rate. The previous slide basically shows this curve.
5 trials.
Yeah, 5
So
trials.
The bars correspond to trials.
Trials, yeah, yes. So separate runs.
Okay.
Yep. It's the standard algorithm in the Met Wi-Fi driver. It's called the ONO algorithm. It's based on the auto fallback. No, it optimizes throughput. So I made it so that the ratios are correct between the bit rates. So you don't, yeah. Yeah.
I have a good feel for what sort of process this is. I mean, there's a lot of congestion in several hotspots from certain types of fields.
Okay.
Are we actually going to get that data as opposed to keeping them
So you can have these 2 models, right? So when you add access point, you can configure them to be their own new cell. And then you can take it to a limit where you have a high density of access points. Each of them have orthogonal frequencies, right? So in that case, you're going to be bogged down with mobility problem, because each time you move, you have to do a handoff. Whereas here, what I'm trying to show is I'm going to try to maintain the cell size the same, but try to improve the packet delivery efficiency within each cell. And then this result suggests that you can, in fact, do better. Your capacity, your achieved capacity is better than a system where you tune them to different frequencies in a hotspot network. Does that answer your question? Or? Yeah.
The other thing is, how does the transpower control
Oh yeah, transmit power control is another big thing. I'm not sure how it would affect the system. I haven't thought about it, but it's going to bring another level of complexity. Because now you have to vary power and vary bit rate and the number of retransmissions. Like there's too many. So for all these, I just fixed the transmit power. Yeah. In some sense, if you tune the modulation, it's almost the same as tuning transmit power. But the reason why I say almost the same is because interference is very different, right? So tuning transmit power has more implication on contention. So that's all I'm trying to say. So, okay. So the reason why, so this box here explains why we maintain a high bit rate. Because the MRD can recover 40% of all losses through the secondary access point, and frame combining can give you additional 7.3%. So it sounds like 7.3% kind of disappointing. That's one thing. And the other thing is, why is the single pass scheme doing so poorly? I mean, this is the question that puzzles me for a while. So what I did is plot the average frame loss rate. I divide the bins into the different bit rates. So at each of the bit rate, I look at what is the frame loss rate when the transmission is happening at the indicated bit rate. So in this example, so this is a mock example, okay? In the ideal world, what you want to see is at a high bit rate, you might expect high losses because the sender is trying to be aggressive. But as you go lower and lower bit rate, you should see lower and lower losses, right? I mean, this makes sense. This is what the modulations are designed for. But then if you look at, if you look at the real data, what it shows is that yes, to a certain point, the bit rates do reduce losses, but then it plateaus out to 20%. It's like, what is happening? Is bit rate adaptation don't work? So just to confirm that with the other receiver, you see the same thing. In fact, to 6 megabit per second, the loss rates are going up. And then if you do this for MRD, what it shows is that at each of the bit rate, it rapidly drops. And it drops to a point when it reaches here, the loss rate never reaches high enough at any single point in time to go even lower bit rate. So that's why I don't have a bar, because MRD had never had to use the lower bit rates at all. So now, why is this thing happening? And this is what I'm going to try to explain. So in this plot here, I'm trying to distinguish two types of loss. One is preamble loss, and the other one is bit error loss. Okay? So in this graph, what I'm trying to say is, what's the fraction of losses that result as preamble losses? Preamble loss meaning like if there's a preamble in each transmission, and that's how the receiver tries to sync up with the frame. And if it doesn't sync up, then you lose the entire frame, no matter what. So what happens here is that you see at the lower bit rates, there are basically mainly preamble losses. So this result suggests that there's an approach to fix the old scheme, the single pass scheme. So the way you should do bitrate adaptation in a single pass scheme is the following: to distinguish between bit errors and preamble errors. And the way you do this is to have the receiver send feedbacks, even though, so send an ACK if the forward transmission resulted in a frame reception, but it's an erroneous one. So if the receiver receives a frame, that implies that the preamble was correct. But if there's error in it, then the receiver should still send an ACK saying that I received your frame, but there's some errors in it. This signal would indicate to the sender saying, okay, I can use the rate adaptation to try to correct these frame bit errors. Whereas there are cases when if the receiver doesn't receive the frame at all, right, then the receiver won't send an ACK back. In this case, then the sender would know, oh, the receiver is not even getting my preamble. So this means that I should probably maintain my current bit rate, but do more retransmission and try to get the preamble through. So this is probably one way to fix it. So this is an idea that I have not pursued, but yeah. Oh, yes. So the reason why there's increase, so all of this I said above is just a theory. So I haven't tested it out, but the theory seems to be consistent with the data. So the reason why this thing is going up, in my belief, is because at these bit rates, the channel is very bad. So there are even more fractional transmitted frames that are suffering from preamble errors. So you're getting more preamble errors. I don't know how to explain this. Yeah. 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 So does that make sense? Yeah. So preamble is, after I see this result, I try to pour into the standard, and then I don't think the preamble is really coded at a certain rate. It's like, it consists of one symbol that uses 12 subcarriers in the OFDM thing. So it's a specialized synchronization sequence that it's the same rate. You can say the same rate, but it's really just a sequence. Yeah. Yeah. Yeah, that's what I thought too, but it's not the case because I'm not getting the frames at all. Yeah. Yep. 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 That's right. No bars because MRD never used that bit rate. It's like right here, it is 20% times 20%, which gives you 4% a loss. And at 4% loss rate, you never have to reduce the loss rate. So MRD gives you that benefit. And I'm proposing a scheme to fix the old. Yeah. No, these are rate adaptation. So I go back to the trace. Yes. Yes. That's what, yeah. Advantageous to transfer 54. Why is that? Why do you say? I don't quite follow. Yes, that's right. So I'm trying to say, maybe I didn't explain it correctly, but I'm trying to say the rate adaptation algorithm assumes that when you lower the bit rate, it would lower the loss rate, right? So, but then once it lowers the bit rate, it still see high loss, so it continues to lower bit rate, which is not the right strategy to use. The right strategy to use is to maintain at 24 megabit per second, but do more retransmissions. Yeah. Okay, so the next set of experiment shows. So I was doing this experiment, wide area experiment, right? And then you can say, okay, maybe I got lucky, right? Maybe I'm testing this thing at a location that is on the edge of both R1 and R2. So maybe, oops, sorry. So maybe I got lucky and I have this corner case where I'm just moving and I'm cheating, right? I'm going between the thing. So what I did is we repeated the same set of experiment, but installed radios that are co-located each other. So now you cannot say that I'm operating on the edge of between the two. And then another reason why we want to look at this case is because, like, do we still get that kind of gain when the radios are close together? So those are the two motivations. So repeat the same experiments, and what we found for the individual, so the first set of results shows just the individual transmission cases. R1.1 and R1.2 is the two different radios that are co-located at R1. And these are the single path transmission scheme. So the surprising thing here is, even though these radios are only spaced 50 centimeters apart, the throughputs are very different. And then if you use MRD, it provides a large improvement despite the fact that they're close together. So in this case, MRD still works when the receivers are co-located. And in this scenario, I'm not going on the edge between the two receivers. So it seems like MRD can still give you diversity gains. And what about R2? R2, we still see similar effects, except MRD2 is now lower than MRD1. And the reason why it's lower because while the co-located radios give you path diversity gains, now you're more susceptible to distance losses because these two guys are co-located, so the distances are correlated. So you're further away from the co-located radios, and that's why you don't achieve the higher result. And for sanity check, I ran the widely separated radio case with R1 and R2, and we see very good results. So the difference between MRD2 and MRD and the widely separated radio case, the difference there suggests that maybe the widely separated radio case has the advantage over the co-located radio, and that is you get better coverage. Does that make sense? Yep. Yep. Except for in time-space codes, you need to synchronize the antenna. Yep. So you cannot do that over the network. Yep. So to illustrate this point more clearly, what I did is I repeated the experiment by moving the test area 1 meter towards R2, closer to R2, and what you see is this new result overlay on top of the old result, and you see R1 getting lower, and that makes sense because you move further away from R1, and you see the MRD experiments for R1 also decrease because you move away from R1. So, but then, on the other hand, MRD, the widely separated radio case, you still maintain high throughput. Just the location of my area, of my test area. Yeah. So I move further away from R1 and then closer to R2. And then you see this shift. So here I'm trying to illustrate that the widely separated radios give you this extra advantage of providing better coverage. And this is where we get the 3x improvement from, as advertised in the abstract. Sorry, I don't know how to spin that. Yeah. Okay. 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 So the next part is, okay, how do we take advantage of transmit side of the system? So here we have, the slide has got mistakes on it. But what I want to talk about is spend 2 slides, really quickly go over how transmit diversity works. And the concept is pretty simple. You use the centralized controller to monitor loss rates at each of the access points at a very fine-grained manner, and you select your transmission over a very fine-grained, do path selection in a fine-grained manner. And the way to make this work is to have the secondary access point spoof the identity of the primary access point, so the transmission happens transparently from the receiver or from the client. And for downlink, you can combine transmit diversity with receive diversity if you can afford to install another radio and run the MRD controller on the client. So typically on an iPack, that might not be possible, but maybe for other more powerful machines or even desktop machines with 2 radios, that is more feasible. And here I'm going to go over quickly the challenges. Challenge to doing this path selection is you have to deal with highly variable channels. And the second challenge is that it's expensive to probe all the channels simultaneously to find the best path. So the solution we took up is a reactive approach. We transmit a current access point, and if the loss rate is higher than threshold, then you switch. So the result here is a 12% improvement over just receiver diversity alone. So transmit diversity combined with receive diversity gives you an additional 12% improvement. And the overall improvement for the downlink direction is 1.5, is a 50%. This improvement is a lot less than an uplink case. Sounds like what's the difference there? So we don't really know exactly what the difference is, other than the fact that the radios on the desktops are much better than the client. So I just want to show this picture because I had a lot of fun hacking my laptop. So what happens is I have 2 receive radios on the laptop, and then for a long time I couldn't get the experiment to show any gains through the secondary radio, and it turns out the problem was the laptop's internal antenna was designed for 802.11b, which is a complete frequency band. So I have to find a hole and then try to string through the antenna and then tape an external antenna. So I just said to myself, I'm not going to let a piece of wire to stop me finishing for my thesis kind of thing. And then this white dongle is the 802.11b thing, so I can launch my experiment while I'm with my laptop. Okay, so that's just distraction. Okay, related work. So there are a lot of physical layer technique, as some of you mentioned. There's MIMO and 802.11n that uses multiple antenna, and I'm not going to belabor it, but our system provides this additional gain over the network. There are soft handoffs in a CDMA network. A soft handoff works basically by connecting your handset to multiple base stations, but in the CDMA network, you're allowed to do this because you have a CDMA type of access where you don't have it in the wireless LANs. And frame combining is based on a really old idea called retransmission with memory. Basically, you try to do frame combining with retransmissions. In MRD, we do frame combining through multiple receive access points, so you get this spatial gain. And then there are many multi-radio wireless systems that you guys have published, so I don't need to go over them. You've done a lot of stuff with management, security, improving performance, so on and so forth, over multi-hop networks. And finally, there's a lot of work in bit rate selection. I believe that MRD provides a really cool platform to reinvestigate some of these algorithms on a system that uses multiple radios. So summary, I've shown that path diversity exists in networks, and I show a system that takes advantage of path diversity. And I have some experiment results that show that my system achieved really good gains. And in future, what I'd like to work on, well, there are 2 things. One is I think there are a lot of extensions that I can make to MRD system, such as rate adaptation, and investigate how to use a centralized controller to do soft handoffs, seamless handoffs, and do that wireless overlay architecture that I mentioned earlier to Victor. And also how to use multiple receive radios to exploit capture effects to improve capacity in network. I can talk more about that offline. And then I'm really interested in wireless networks in general. I enjoy building systems a lot. Things like mesh networks and vehicular networks really fascinates me, and like to work on all of the areas that are shown. So basically, this is my talk.